separately. However, we cannot, from each component, derive an ideal design that will minimize f sub q. Still, solving this problem shouldn't be too difficult, right? It's just a matter of mapping the interaction between each component to produce a total model for f, which we can then minimize. This sort of thing is covered in heat transfer all the time. It's just a basic energy conservation problem, so we can solve that now, right? So in order to solve this problem, we first have to define the problem. That is, we have to draw a general greenhouse design with several variables left undefined, and then solve those variables for the minimum f sub q. We begin simply with the basic structure, defining the greenhouse as an enclosure, bearing in mind that not all surfaces inside the greenhouse react to incident light in the same way. For instance, the concrete of the floor will likely have an extremely different incident property than the plants themselves, and so what fraction of the greenhouse is the outer wall of the greenhouse is a heat flow circuit with parallel resistors shown to the right. Keeping in mind that these properties will change as the overall plant coverage and other shape factors begin to change, and bearing in mind that the circuit will have a different property for each frequency of radiation owing to the different incident properties, we can determine this by calculating the total convective resistance between the wall and the air in the greenhouse, depending on current air velocity assuming static conditions. Okay, so maybe it's not as simple as we portrayed it. Unlike the problems in heat transfer that undergraduates solve on a regular basis, a greenhouse is not a simple system. The wide variety of surfaces inside interact with the light coming into the greenhouse as well as each other to produce extremely complicated radiation interactions. Furthermore, it is not reasonable to assume that everything in the greenhouse is necessarily the same temperature. Hot air rises, which means that without constant artificial circulation and proper interior geometry, it will quickly develop a vertical heat gradient, which means that any heat equations that depend on the air all being the same temperature, particularly those with regards to window placement, will produce inaccurate results. The floor can also develop hot or cold spots, particularly as increased plant cover causes shading. The complexity of this problem quickly grows so great that the effort involved in creating a proper engineering model of an entire abstract greenhouse in order to optimize it would cost more money than you would save by optimizing it. With that in mind, our goal in modeling becomes to find a way that we can make approximations and simplifications without significantly decreasing the accuracy of our result. So let's review. First, we defined the structure of a greenhouse to be the components of the greenhouse which do not expend energy. We chose this definition because our goal in designing this structure is to minimize the level of active energy expenditure required to maintain stasis conditions inside the greenhouse. We represent this expenditure with a function f sub q, which is a measure of the net energy outflow of the greenhouse at any given time, assuming the greenhouse is operating at its stasis temperature. The reason we select f sub q instead of the alternative function f is that f sub q can be calculated without regard to the interaction of separate components, and is a more accurate representation of what we wish to determine. We can therefore more precisely define our structure design goal as seeking to minimize the integral of f sub q over the greenhouse's standard operating period. For a completely quantified greenhouse design, we can automate this process and do so, as it will greatly accelerate our ability to check the validity of other designs in the future. The power to compare the quality of our design against all the available data over the operating period, instead of just the averages as a human checking by hand would have to, also increases the accuracy of this evaluation. However, we discover that this evaluation does not run backwards. Although we can very quickly find efficiency and f sub q values for a known design, we cannot use this formula to go backwards and derive the most efficient possible design from given parameters. We therefore seek to find a number of evaluations that make this solution solvable without sacrificing accuracy. The juxtaposition of these approximations and our ability to precisely calculate efficiency for a known design then becomes the basis of structure design in CEA. In this manner, we are able to go back and forth, developing different approximations in order to attempt to solve for an ideal design, and then plugging that ideal design into a computer in order to calculate its final efficiency value. No computer model is perfect, and so real-world testing will always be required. However, by this cycle, more efficient greenhouse designs may be generated. Future videos will cover this cycle in more detail, giving you an understanding of possible features that can be added to a structure, a little bit of heat transfer so you can calculate F sub Q, and a run-over of basic material properties of common greenhouse materials, as well as common approximations that are used for calculating greenhouse conditions.